Hey y'all. This week we're going over the inverse of log and exponential functions. So if you open up OneNote, you'll see these notes in your week 2 notes. Under the content library, you'll see mine, and you could fill in and follow along on your notes. So as you can see, we have the basic function of an exponential right here, and that's f of x equals the base to the power of x minus h plus k. And on this side, we have a basic function with the transformations of a log. So we've got f of x equals log of base b of x minus h plus k. So we're going to compare some of the attributes of each function and see where we're at. So we're going to do 1 and 5, then 2 and 6, and so on. So what kind of asymptotes do exponential functions have? Well, if we were to look at a graph of an exponential function, we would know that they have horizontal asymptotes. Logarithmic functions have vertical asymptotes, so they're opposite. Exponentials have horizontal, and logarithmic functions have vertical asymptotes. So now we're going to look and see where we could see this actually in the equation. For exponential functions, we see it with this plus k value. That's how you find your horizontal asymptote, is in the plus k value, which is, as we know, it means that it's shifting our function up or down. So if we have a horizontal asymptote, we see that in our shift because it's going up or down. So with our vertical asymptotes for our log functions, we're going to see that with the h value, which represents the horizontal transformations. So you'll see that right here, whatever number is right next to the x value. Hopefully this is ringing some bells from the Delta Maths that y'all did last week and before finals, that's how you find your asymptotes for your log and exponential functions. So we're going to scroll down to the next section. We're going to figure out how we write our asymptotes for each of the functions. So if we know that our asymptote for exponential functions is our k value, and we know that it's horizontal, that means our line for our asymptote is y equals k. And we know that our asymptote for our log functions is this h value, and we know that it's a vertical asymptote, so it's got to be an x equals line, and it'll be x equals h. So now let's look and see what the domain and range of each of the two functions would be. The domain for exponential functions is all real numbers. So we're going to notate that now. Domain equals all real numbers. Our range in interval notation is from our k value to infinity, because our range, remember, talks about the y value. So if we had a horizontal asymptote, it would be from that horizontal asymptote and up. Our domain and range for logarithms is exactly opposite. Our domain is our h value to infinity. So if we were to see a function or a sketch of that, it would look like this. Here's our asymptote. Here's our log function. It would start at the asymptote and go towards infinity. And our range for all logarithmic functions is all real numbers, or from negative infinity to positive infinity. So as we can see, all of our log and exponential functions are exactly opposite of each other, right? We've got horizontal asymptotes versus vertical asymptotes, the k value versus the h value, y equals k versus x equals h, and then the domains are exactly flipped of each other. So what does that mean for their relationship with each other? It means that they are inverse functions. So a log is an inverse of an exponential and vice versa. So now we're going to talk about two ways that we know how to verify or to solve for inverse functions. So the first way we know how to solve is to switch the x and y values that you see, and then to solve for y. The second method that we know to solve for inverse functions is by using composition of functions, which looks like this. When you have one function that you're plugging into another. So f of g of x would be this example. So now that we know exponential and log functions are inverse functions of one another, we are going to solve some examples. So let's scroll down to the examples page. So starting with number 1, we have y equals log base 3 of x. So we're going to solve most of the ones on this page by switching the x and y values. So let's start with the first one. So instead of y, we'll have x equals log base 3 of y. So all you're doing is switching the placement of the x and y values. Now let's label this. We know that our base is 3. We know that our exponent is our x value, and that our answer, once we put it in exponential form, will be y. So now let's write this in exponential form. Our base is 3, our exponent is x, and that equals y. Since y is all by itself, that means that 3 to the power of x is the inverse of y equals log base 3 of x. Number 2 is y equals 3 to the power of x. Well, we just solved for the inverse of it, right? So we're going to use composition of functions now to verify that y equals 3 to the power of x is the inverse of y equals log base 3 of x. So since in the last problem we said y equals log base 3 of x is the inverse of 3 to the power of x, we're going to plug in 3 to the power of x into the function log base 3 of x. So now this is what we have. So now what we're going to do is we're going to rewrite this in exponential form. So we're going to do that by labeling our base, our exponent, and what the answer should be. So once we have everything labeled out, we know that our base is 3, is risen to the power of y, and that equals 3 to the power of x. Now think back to a couple weeks ago when we were talking about exponent rules. When two things are equal to each other with the same base, you could just set your exponents equal to each other. And we know that when we're looking for inverse of functions, by using composition of functions, we could verify that they are inverse if the composition is y equals x. So we know that we did number 1 right because we confirmed it with the number 2. Now for number 3 and 4, we're just going to go into it with switching x and y. So I'm going to scroll down a tiny bit. All right, so we've got y equals log base 2 of x plus 4. So the first thing that we're going to do is switch the x and y value. So I'm going to have x equals log base 2 of x plus 4. Nope, of y plus 4, I'm sorry. We're switching for the x's with the y. They're just switching places. Now, since this plus 4 is not in parentheses, it's not included with this log, we're going to get rid of it. So we're going to subtract 4 from both sides. Now we have x minus 4 equals log base 2 of y. So now we've got our log isolated. I'm going to put parentheses around my x minus 4 so that way I know that that's together. That's like one unit. That's one thing. And now let's label our base, which we know is 2. Our answer will be the x minus 4. And the, oops, nope. I'm sorry, y'all. The exponent is going to be the x minus 4. And the answer is going to be y. So when we rearrange it into exponential form, we'll have y equals 2 to the power of x minus 4. And the whole x minus 4 is the exponent, so that's why it's all risen to the power. Since y is now by itself, we are done solving for this inverse function. So now looking at number 4, we're going to do it the exact same way. We're going to start by rewriting our function as x equals 5 to the power of y minus 3. So we're switching our x and our y. And now we need to solve for our inverse. So we're going to solve for y by rewriting it in in logarithmic form. Since this is already in exponential form, we're going to write it in logarithmic form. So our base is 5. So let's start by labeling. Here's our exponent. Here's our base. And here's the answer. So if we were to write it in logarithmic form, our answer is the y minus 3. That equals log base 5 of x. Remember, whenever we're switching x and y, the goal is to solve for y, so we need to get y completely by itself. We've got this plus 3, or this minus 3, so we need to add 3 to both sides to cancel it out. We'll add 3 to both sides, and we get y equals log base 5 of x plus 3, not in parentheses. All right, let's do number 5 now. So number 5 does have parentheses. Since there are parentheses around this x minus 1, we cannot add 1 to both sides because it is included. It's y equals log base 4 of x minus 1. So we're just going to go straight from here to converting it to logarithmic or to exponential form. So our base is the 4. Our exponent will be y. And the answer So we also have to switch x and y first. So that's what we're going to do first. And now we're going to convert it to exponential form. So our base is 4 and our exponent is x. That equals our y minus 1. Now we want to make sure that y is completely by itself. So we need to add 1 to both sides. And we'll get y equals 4 to the power of x plus 1. And I want you all to notice that this plus 1 is a big plus 1. It's not the tiny one that's next to the x. This represents a vertical shift. Remember that the little one represents a horizontal shift. So we'll look at number 6 now. First step is to switch x and y. So we'll have x equals 2 to the power of y plus 7. Since this plus 7 is big, it's on the outside, we can't do anything with it until we get our exponential completely by itself. So we're going to subtract 7 from both sides. Now we have x minus 7 equals 2y. Now that our exponential function is, or exponential is by itself on one side, we can convert it to logarithmic form. So we'll have log base 2 of this x minus 7. This is staying together as the answer, so it needs to stay in parentheses once we convert it to log form. And that equals our exponent, which was y. So the inverse of y equals 2 to the power of x plus 7 is log base 2 of x minus 7 equals y. All right, we're on our last two problems. Woohoo! So let's jump right into 7 with switching our x and y value. So we'll have x equals log of x plus 1. Now I need to convert this into exponential form. Sorry, that should be a y. All right, so I need to figure out what my base is. I don't see an actual base there, which means that this is the common log. And the common log is a base of 10. Our exponent will be x, and that's set equal to y plus 1. Now we know that we need to get y by itself, so we're going to subtract 1 from both sides. So I'll have 10 to the power of x minus 1 equals y. And that is the inverse of number 7. Number 8 is a little different. We have y equals e to the power of x. I want you all to remember that e is just a number. E is approximately 2.71 and then a whole bunch of other stuff after. So e is just a number, but however, it has a special log. So let's start by just switching x and y. So when we switch x and y, we have x equals e to the y power. Instead of log base e, e is kind of like a common log too. So whenever you don't see a base with log, you know that your base is e, or your base is 10. So the base that goes with e, the logarithm that goes with e, I'm sorry, is the natural log. I don't know why they switched the letters for natural log, but ln is the log of e. So whenever we're rewriting this, let's label all our stuff. We know our base is e, which means we have to use natural log. Our exponent is y, and our answer is x. So we know that we have to use natural log of our answer, which is x, and that has to equal our exponent, which is y. So our y is all by itself now. So the inverse of y equals e to the power of x is the natural log of x equals y. So natural log goes with e to the power of x. So whenever you see e or natural log, you know that you need to use the natural log or that your base is e. All right, please continue on with the rest of your Delta Math assignment. If you have any questions, I have tutorials most days. And I will see y'all real soon. Have a great day. Bye.